All right, so this is for my students. So we are talking about properties of logarithmic functions. So this is like the next area that we're going to be working in, and we'll see later on how this is sort of connected. So right now, it's probably going to feel kind of new. It is kind of like a new way of how we solve equations, and that's going to actually prove to be super useful, not only at one point but also at multiple points. So knowing how to do these next few properties is going to help us in the long run. So when it comes to logarithms, we have sort of, again, it's the inverse of the exponential. And so what that entails is the arithmetic that we're going to be doing with expressions in general, is it's going to offer us a new way of solving things. So the rules are a little weird, but the faster you get used to them and sort of the more you see it, the easier it's going to make our lives. So, okay. We're going to start with the product rule. The product rule. Okay. Now, the emphasis here is the fact that, so let's see here. So let's say we had log of 6. Log of 6 we can rewrite as, if I look at its factorization of 6, I can write this as the log of 2 times 3. Why is this significant? Well, when it comes to logarithms, this is going to be equivalent to saying log of 2 plus log of 3. So we can change something that was a simple statement and basically expand it into simpler terms. So log of 6 is the same as log of 2 plus log of 3. And so this is what's known as the product rule. So if I have a log of any multiplication of numbers, then it's the same as if I broke up those two factors and added their logarithms together. Okay. So what's an example of solving? Let's look at an example of simplifying something. So if I gave you the expression log base 2 of p cubed plus log base 2 of q, then the product rule says, so not only if I have the product of a number written as its, with its factors is the same as the sum of the logs of the factors, but I can also go backwards. If I was given 2 logs that have the same base and 2 numbers within those, I can just multiply them and write them in a single logarithm. So log base 2 of p cubed plus log base 2 of q is going to be equal to exactly their product, or p cubed times q. So that's going to be equivalent. So basically, if we have whatever numbers are here and the bases are the same, then what we can do is simply combine them and multiply them together. Next up, we have the power rule. The weirdest, I think this one. Let's say we have the logarithm of 8. So if I was going to rewrite this, right? Well, let me look at the factors of 8. Well, 8 is the same as 2 cubed. Now this power here, what the power rule does, it allows us to pull this out and bring it up front of the logarithm. And so log of 8 is going to be equal to log of 2 cubed. Well, that's the same as 3 times the log of 2. So that's the power rule. So I could change something that had log of 8 and I decomposed it into its factors and I found that it was a cube. So it's the same as if I multiplied log of 2 3 times. Next up is the quotient rule. Okay, so quotient rule, just like with multiplication, well, if I have a log of division, so if I have, I don't know, like 2 over 1 or 4 over 2, whatever it may be, then this is going to be equal to the difference of the logarithms. So I could just take log of m and subtract log of n. And there we go. These are equivalent statements. All right, let's take a look at this log, which is kind of complicated, but the reason why it's complicated is because we're going to undo this and make it bigger and make it like use the logarithm laws or the rules. So, okay, so we have to combine a few different things, what sort of makes sense, right? Let's see. So we have log base a of this. So I can actually rewrite this radical, as I know from properties of exponents, that if I have a times b over c squared, I can basically, this is the same as raising this to the 1/3. Okay. So actually, this is not equal to, but I'm rewriting this logarithm like this. Okay, and then now I'm going to use that power rule, which allows me to take exponents out and multiply the logarithm out. So this is the same as log 1/3 of log a of ab over c squared. Okay, so I see some quotients and I also see some multiplication. I'm going to handle the quotient first because I think it's a little easier that way to see what's going on. So I'm going to break up the numerator with the denominator. So I'm going to have 1/3 times log base a of ab minus log base a of c squared. Okay, that's quotient rule. And last but not least, I have a times b. I'm going to use the product rule to once again expand this logarithm. All right. And you'll notice we have a log base a of a. Well, a raised to what equals a? Well, that's just 1. So I can actually rewrite this more simply like this. So we have 1/3 of 1 plus log base a of b minus, 2 log base 2 of c squared. And boom, there we go. So we rewrote this whole logarithm, which is right here. We started with this, and we ended up with something a lot more complicated with 1s and 2s. But yeah, this is how we use logarithm properties. Okay, so as we stated before, the exponential f of x equals 2 to the x. Its inverse is going to be precisely the logarithm, log base 2 of x. So we're switching the x and y's, and that's exactly how we find the inverse. Now we're going to be talking about what it means to compose a logarithm with its inverse, the exponential, and how we can also flip it and use this to our advantage to solving logarithmic equations and problems. So for instance, if I take a function and I compose it with its inverse, then we know exactly that the result has to be x. Not only that, we also know that if we do it backwards, it's also equal to x. And that's important because how do I write f of f inverse with using exponentials and logarithms? Well, all I'm going to do is take the inverse, which is log base 2 of x, and raise that above 2. So we get log base 2 of x. On the other side, if I took the exponential and plugged it into the logarithm, that would be like that's like composing f of x with the inverse. So I'm composing the exponential with the logarithm. And that looks just like this. Log base 2 of 2 to the x. All right, well, with our equation here, we say this is equal to x. So whenever you see something like log base 2 and this, so essentially if the base of the exponential is the same as the base as the logarithm, if the logarithm is in the exponent, then we know we can just take these, basically cancel these out, and we're left with x. And then on the other side, when we have a logarithm with the same base as the exponential inside of it, then we know we can also erase those. The x drops down. the weirdest. I think this